time for us to do some practice involving separable differential equations. The basic idea is pretty straightforward, and so we're going to go at a pretty good clip as we get going, because how do you do it? Remember, there's 3 steps. You separate, and hence the name separable differential equations. You integrate, and that's, well, integration, no surprise, because we're solving a differential equation, which basically means we have to find some sort of antiderivative. And the last thing is uncomplicate, which means that we solve for a constant, solve for our function, or some combination thereof. So as we get going, you'll see these problems go pretty quick, and once you get the rhythm, it's wonderful. These are fantastic problems and lots of fun to deal with. So do lots of practice. You'll get pretty good at it. Let's get going. So our very first problem says, find y given that y prime equals y squared plus 1 and y of 0 equals 1. And then there's the second part. Determine the interval for which the solution is valid. In other words, when you solve a differential equation, you can say, okay, I have this expression. When is it true? So we'll get to the second part later, but let's just do the first part right away. Okay, so what do? Well, first off, we say it's a separable, and I will say, yes, spoiler alert, everything's going to be separable today. But what do we see? Well, we have this differential equation, which we could rewrite if we think of y prime as dy over dx. dy over dx equals y squared plus 1. And notice, when there is no x at all, it's always going to be separable. And because you can just put everything, the dy dx on one side, all the stuff on the other side, the other stuff I should say, and then just divide. By that I mean, hey, this is really the same as dy divided by y squared plus 1 is equal to dx. And now we've done our separation. All right, great. Well, what comes next? Next step is integration. So integrate. All right, integral of dy over y squared plus 1. One of our favorite integrals. That's arctangent of y. So arctangent of y. All right, integral of dx. Well, that's x. And then don't forget plus c. Good. Now, we're 2/3 the way done. We're doing pretty great. Now, the last thing is to what we call uncomplicate, which really means, okay, solve for y and or solve for c in some order, right? Now, in this case, we will solve for c because we are given an initial condition, y of 0 equals 1. So that means we need to figure out, all right, what is the appropriate choice for c? Now, you can always solve for c first and then solve for y, or vice versa. It just depends on the context. Now, in this case, let's go ahead and solve for c right now. We can do that. What do we have? Well, we say, look, when x equals 0, we'll have that y equals 1. So that's our initial condition. So arctangent of 1 is equal to 0 plus c, which tells us that c is arctangent of 1. Well, do we know some angle, or the tangent of that angle is 1? And there's such an angle, it's pi fourths. And so arctangent of 1 is pi fourths. So now we're like, great, we know what c is. So updating, we say, okay, arctangent of y is really x plus pi fourths. And now, to get the arctangent removed, to take it out, we use the fact that it's the inverse tangent function. So we'll use the tangent function. Tangent and the inverse tangent function will undo each other. And so we get y is equal to tangent of x plus pi fourths. All right. Good. There we go. Done. All right. Well, what's the first part? There is a second part, right? Which is to determine the interval for which the solution is valid. Now, what are things that could go wrong? Now, some things can go wrong in the actual differential equation. So in other words, if we come back here to our differential equation, we could say, oh, the right-hand side isn't defined, something is blowing up. there's a place where this is not continuous, or the derivative with respect to y is not continuous. None of that's happening here. So we say, okay, look, there's no problems from the differential equation, but there might be problems from the solution in the sense of there's asymptotes of some sort, or some sort of vertical tangents. Now, the function tangent has vertical asymptotes, lots of them actually. And so what's the problem? Well, the problem is that our solution can only go up to a vertical asymptote, can't go past. So these vertical asymptotes are sort of bars that stop us from continuing on. And remember the philosophy. Why is that? Well, because we're trying to say, look, the differential equation is telling us how to move. And so we cannot move past these asymptotes. They're boundaries. And so that's why we can only go up to a vertical asymptote. So our solution, we're going to be valid up to our nearest asymptotes. Okay, so that's the key idea. So the real question becomes, well, where are those asymptotes at? So valid up to our nearest asymptotes. So let's think about, where does tangent have asymptotes at? Well, at pi over 2. That's our first asymptote, right? What is tangent pi over 2? Some people say, well, it's infinity. Well, it's undefined, because if you were to graph the tangent function, so this is tangent of x, you'll see that it looks something along the lines of the following. We'll extend it a little bit here. So here is pi over 2. Here's negative pi over 2. And it comes up like so. And of course, there's other asymptotes. 3 pi over 2 minus 3 pi over 2, so forth and so on. There's infinitely many of these things. So that's what our tangent function looks like. So we start to say, okay, well, where's going to be our problems? Well, we're going to have problems when our input looks like where one of our asymptotes is at. So say, okay, what does that mean? Well, we're going to have asymptotes at where x plus pi over 4, that's our input, is at pi over 2, or at negative pi over 2, or any one of those. But we only need to care about the closest ones. So notice we're at x plus pi over 4. So there's been a slight shift, but not a big shift. So we're really going to be focused on these two. Those are our nearest asymptotes. All right, well, so what do we have? If we have x plus pi over 4 equals pi over 2, that says, okay, one thing that could happen is at pi over 4. That's going to be a problem, because at pi over 4, we have pi over 2 trying to be plugged in. Whoa, okay, there we go. And what about here? Well, negative pi over 2 subtract pi over 4 would be negative 3 pi over 4. Now, there's other ones as well, but in terms of our function, if we think about what's happening with the tangent of x plus pi over 4, what's happening is that there's a horizontal shift to the left, right? So we're shifting everything over by pi over 4. So that's what happens. So that our asymptote that was at pi over 2 switches to pi over 4. The one at negative pi over 2 switches to negative 3 pi over 4, so forth and so on. And so these are our nearest two asymptotes. These are our two boundaries. So where's the interval where it's valid? Well, in between these two. So we can say, look, valid from negative 3 pi over 4 all the way up to positive pi over 4. And there we go. There we go. That's the solution where it's valid. So when you're looking for where a solution is valid, look for either problems with the original differential equation, or look at your solution and say, hey, where do I have asymptotes? That's going to be a limiting part. All right. Okay, good. Whew. Done. The actual differential equation, by the way, was probably pretty straightforward. It was just like the reasoning, okay, how do we get to the place where it's valid? That was a little bit more subtle, but it's good to do one of those once in a while, right? Yeah, of course it is. Of course it is. All right, well, let's do another problem. Okay, so we've talked about this before. This is Newton's law of cooling. So find T, so we're thinking T here as temperature, given that T prime is minus K times T minus A, where K and A are constants, and T of 0 is T0. Okay. Now, remember the setting here. So capital T is temperature, because we're talking about objects heating or cooling. Little a is the ambient temperature. So what is that? Well, what you can imagine here is you have some sort of a, say, refrigerated space, and so it's very cold. That's why it's blue, because it's cold, right? And so we have this cold environment. It could be a hot environment too. It doesn't matter whether we have a cold or a hot environment, but we have this environment, and inside of here we put an object. It's very hot, and you can tell it's very hot because it's red, so it's been heated up. And the question is, well, what happens to this object over time? So that's the question. That's what Newton's law of cooling is looking at. So T minus A is the difference in temperature between the current object and the ambient temperature. And it says, look, the larger that is, the faster the change will occur. And now what is K? Well, K is a constant. It's kind of essentially a fudge factor. Say, well, based off of the heat transference properties of the elements involved, this is what happens. So it's basically a fine tuner. It says, okay, how quickly does this object absorb the ambient temperature? It might absorb very quickly, might be very slowly, it just depends. And here, this T0, that says, what's the object at time 0? What's the initial temperature? Okay, so those are all the pieces. And now we want to solve. Say, okay, great. Well, is this separable? Yeah, it is. Because notice, the only variables that show up are capital T. There's none of the dependent variables, or rather, the independent one, the time we think of that. So yeah, we can always separate this. So we should think of this as the change in temperature with respect to time is minus K times T minus A. Or we could say, okay, separating dt, change in temperature, over T minus A, is minus K d lower t, change in time. All right, great. That's the separation. Now the integration. Integrate. Okay, well, what do we get? On the left-hand side, we'll get natural log of T minus A. All right, over on the right-hand side, minus KT plus C. Yeah, that was pretty quick. Integration, not so bad here. All right, well, let's keep going. Let's solve for capital T. Okay, so what is that? Let's get rid of the log. So how do we get rid of log? Well, use the inverse function to log, which is e. So that becomes T minus A is equal to, and over here, well, it's e to the minus kt times e to the c, because this addition up in the exponent becomes multiplication. And now we say, oh, well, e to the c, that's e to a constant, that's a constant. And so we say, okay, great. Well, we can write that as some new constant. We'll still use c because we're recycling at this point. A little bit sloppy, but that's all right. E to the minus kt. Okay, good. Now, you might have some questions here. What happened to the absolute values, right? Why do you just write t minus a? Here's why we can get away with this. The reasoning here about why we can do this is to say, well, look, you see this c? I didn't actually specify c was positive, so I'll allow the case for c to be negative as well, and that lets me drop the absolute value. So that's one way to justify it. The other reason is a bit more complex. We'll get into that kind of reasoning as we go on throughout the semester. All right, great. Well, we're almost done. So what do we get? Well, solving t equals a plus c e to the minus k t. All right, so we're well into our uncomplicate phase. What's left? Well, we need to solve for our constant c. So at this stage, we say, all right, let's use our initial conditions. And namely, we have when time equals 0, we can say, look, our temperature is T0. All right, so T0 is equal to A plus some constant C, e to the minus k times 0. All right, well, the nice thing is e to the 0 is 1. So that allows us to say, aha, C is equal to T0 minus A. And put that in for our C, and we come to the conclusion that our temperature here behaves like our ambient temperature plus T0 minus our ambient temperature, e to the minus k t. And we're done. That's it. So that's how it works. We went from, hey, here's this expression, and we found our formula for temperature. And you'll notice it works kind of like what we think it should work like. If you graph this function, what do you see? Well, you see there's this ambient temperature. And now you say, well, look, if your temperature is above your ambient temperature initially, then it's going to start to go down. And it behaves like an exponential function. So, in other words, it will decrease most rapidly when there's a greater temperature change. So it's going down faster than it'll start, but then it starts to sort of slowly approach. On the other hand, if our temperature were below our ambient temperature, well, we would be going up, and in the long run, again, we're going to approach A, but again, same sort of exponential thing going on. Now, on a side note, as a freebie, this actually is going to be essentially the same model that we see with exponential growth and decay. So if you look at the case where A equals 0, well, what is that? Well, that says T prime equals minus K times T. Well, then what do you get? Lo and behold, we get that our temperature, well, is what? T0 e to the minus k t. And so this is the model that's used for things like radioactive decay. And it's this formula. It's the same basic exponential change. So we see that happening. It's also, look, we really don't care about the sign for k. K could be positive or negative. So if this had been positive kt, well, we would have e to the positive kt. All right. And now that's a model for population growth. Very simple model. And so, yeah, you can get all these wonderful things coming out. So, yeah, there you go. Aha, Newton's law of cooling. Done. Done. All right. Well, let's try an example. In fact, we're going to use Newton's law of cooling here. And so here's our problem. A 4-pound roast, initially at 50 degrees Fahrenheit, is placed in a 375 degree Fahrenheit oven at 5 p.m. After 75 minutes, it is found that the temperature, so temperature as a function of time, of the roast is 125 degrees. When will the roast be 150 degrees? Now, that's what's considered to be medium rare. Probably, hopefully, that means that's going to be tasty. Okay, well, let's see. What do we have here? Well, we have lots of pieces here, so we have to sort of look at things. So we have the roast, and the roast is what's changing. See, the oven is at 375, so that's the environment. So this 375, that's our ambient temperature. So we say, okay, great. Our ambient temperature equals 375. And we'll drop our units for the time being. And now we have the roast. Well, look, it says, look, our roast is at 50. Okay, so the roast is what's changing temperature. And so we have at time equals 0, our temperature is 50. So this is our T0. And now we say, look, at time equals 75, right? After 75 minutes, so our our temperature after 75 minutes is equal to 125. And now our goal says, look, at time equals something, we want our temperature at that time to be 150. Okay? So that's our goal. So here, our goal is to say, what is this? What is that time that gives us what we want? Okay. All right. So we have our pieces. And the good news is, say, look, we don't have to reinvent the wheel. This is Newton's law of cooling. Okay. So what do we have? We have our change in temperature is minus K times our temperature minus our ambient temperature, which is 375. Now, we don't know what K is, and that's part of our problem. We'll get to that in just a second. And now we say, hey, we know by Newton's law of cooling that since we know our initial temperature here, that our temperature at any given time t is going to be equal to our ambient temperature, 375, plus, all right, let's come back here just so we remind ourselves, our ambient temperature plus our initial temperature minus our ambient temperature, e to the minus kt. Okay, so that's going to be 375 plus our initial temperature, 50, minus our ambient temperature, 375, e to the minus kt. All right, well, that's really 375, and then we're going to have minus 325, e to the minus kt. Now, what do we want? And what have we used? Well, let's mark what we've used. We've definitely used the fact that we have our ambient temperature 375 and our initial temperature is 50. That shows up. We haven't yet used this information, our temperature at 75. Say, okay, well, why would we need that? Well, you'll notice there's this constant K. So K depends on the situation, and what we can do is we can extract what the K should be by using information about what's actually happening as we do our cooking here. So this time measurement at time 75 being 125 degrees is going to be helpful because it'll let us extract what the value for K is. All right, good. And so let's do that. So we can say, okay, great. 125 degrees is the temperature at time 75. All right, so that's equal to 375 minus 325 e to the minus k times 75. And, well, okay, so we can do some moving around. And we can say, all right, 375 subtract 125 would be 250, right? So 250 is equal to 325 e to the minus k times 75, or we do some division, e to the minus k times 75 is equal to 250 divided by 325. And now we say, oh, okay, well, these are kind of unusual numbers, but they're both multiples of 25, right? So if we divide top and bottom by 25, well, the upstairs would be 10. Downstairs, well, that's a little bit more tricky, but what will happen is we can think of it as 250 plus 75, so that's 3 more multiples of 25, so that's 13. So 10 thirteenths. All right, so we want to get K. Right now it's upstairs. So what do? Well, all right, we can do something, namely use logs. Yeah, there's a lot of logs that go on in this kind of problem. So minus K times 75 is equal to natural log of 10 over 13. Now, finally, to get k, we can say, okay, great. So k is minus 1 over 75 natural log of 10 over 13. And I'll just leave it like that. There's not really much we can do to simplify. You might start to be a little bit nervous here because in the back of your head, there might be something saying, hey, wait a second, hold on. I thought k was positive, but I see a minus sign saying that k is negative. Well, be careful. Just because you see a minus sign, does that mean that the number is negative? It does not. And here's where the be careful is. Notice that we're taking a log of a number, and 10 over 13 is a number below 1. And the reason that that's important is because that says, okay, log of a number below 1 is actually a negative number. So really, there's a negative and another negative, and so this whole thing is a positive value. So k is actually a positive value. All right, so what's happened here? We said, aha, this additional information at a different time, this part we were able to solve for k. So now we're like, well, perfect. We have a complete expression. We can tell our temperature at any given time. So given that we can do that, we can say, well, hey, now let's set our temperature to 150 and figure out, well, what time does that correspond with? So here's the last part. All right, so we say, okay, great. We'll leave it as t instead of question mark, question mark. But we'll say, okay, we want 150 to be our temperature at time t. So we're solving for this time, and well, that's got to be equal to 375 minus 325 e to the minus kt. And I do know that minus kt has this expression here. I'm just going to, because this is a long to write, I'll just leave it as k for the time being. All right, well, we do what we did before, right? We move stuff around. So we say, okay, great. We can move terms around. We can say, okay, well, this really is the same thing as saying 375 subtract 150 would be what? Well, it's 225. And that's going to be equal to our 325 e to the minus k times 75. All right, great. Whoops, not 75. Ha ha ha. That's t, excuse me. Right, k times t. There we go. Yeah. All right, well, divide. 225 divided by 325. Well, we would have e to the minus k times t. Now, we can do the same thing that we did before, namely factor out 25. You know, that's a nice factor. And we get that's 9 over 13. And so we say, great. Taking natural log minus k times t is equal to natural log of 9 over 13. Or we can say, look, what is t? T is equal to minus 1 over k times the natural log of 9 over 13. And in some sense, that's our answer, because we know what k is. K is this expression here. And so if we put this all together, we can actually combine this value for k, for that value of t, and we can say, aha, our answer, all right, so we're taking the negative reciprocal, so it would be 75, that's that reciprocal there, and then we'll have a log of 9 over 13, and downstairs we'll have a log of 10 over 13. Right, that log of 9 over 13 came from there, and then log of 10 over 13 came from there, because remember, we're flipping it. That's that 1 over k action. And now that is our time t. And this is a wonderful chance for us to go grab a calculator, and because, well, there's not a lot of people who know log of 9/13 or log of 10/13 off the top of their head. I happen to have done the computation earlier, and so I can tell you that this would be 105 point something something something. So that tells us what? Well, that says after 105 minutes. Now, our question was when? Okay, so we can give an answer after 105 minutes, and we can even set the actual time, right? Because we start at 5 p.m. 105 minutes will be 60 minutes, which is 1 hour, plus another 45 minutes, saying, all right, so the time we should have it done is at 6:45. So there we go. At 6:45, our roast will be medium rare. And we're done. We're done. Good. Now, we should pause for a second here and just have a quick discussion that says, hey, whenever you're doing a problem, you should always look at the end and say, is this reasonable? So what do I mean? Well, we should say, okay, what's happening here? We know that after 75 minutes, we were able to warm it up by 75 degrees. And so how much additional time does it go for the next 25? Well, we probably have seen cooking before. We know it shouldn't take hours or months, but it should take some amount of time. And remember, the temperature change is always greatest at the start, and then the temperature change starts to slow down. Now, that's what happens when you have this sort of exponential behavior going on. And so, say, okay, well, how much additional time did it take us? Well, it took us an additional half hour. So the remaining 25 degrees took us about 30 more minutes. It says, okay, that feels about right. If we had done the computation and we had said, oh, it's going to take another 5,000 minutes, we would know that something had gone wrong. And we would stop and say, let's backtrack a little bit and let's check our work, because we know how things operate. Things should not be crazy numbers like that. But a lot of students, and when I say a lot, I don't mean to say the majority, but I have seen this in the past where people are just like, I don't need to think about what these problems represent. I'll just blindly put an answer on it. So many years ago, I taught a course in trigonometry, and there was a problem about finding the height of a mountain. And if you did the problem right, it was something along the lines of like 3 miles and change. And one student, casually wrote down, oh, this mountain is 11,000 miles high. What? 11,000 miles? That's crazy. I mean, Mount Everest is on the order of 7 miles high. To say, oh, here's an 11,000 mile high mountain, you should be highly suspect that something is wrong. And so there's a wonderful time to say, hey, I know things. Let me use my intuition and my knowledge about the world to say, is this a reasonable answer? Because if you don't have a reasonable answer, it's a signal to you that says, something probably happened here. Let me back up and let me figure out what it was, so that I can make sure I give myself all the points, right? That's our goal. We want to do well. We want to make sure we get all the points. But more importantly than having the points, of course, the understanding. We want to understand things. We value that. We highly value being able to understand. All right, good. On a side note, I think this is the only problem that requires any calculator to get the final answer, at least for today. But it's not too bad. Not too bad. You'll see lots of these problems, by the way, where this is similar to problems where they talk about, oh, there's radioactive decay going on, or some sort of radioactive or some sort of population growth going on. Where they say, okay, well, I'll give you 2 pieces of information. What's happening at some time and what's happening at some later time. So it might be minutes. If it's radioactive decay, it might be thousands of years, just depends. And the reason they're giving you a second time measurement is to solve for k, because we always have that sort of fudge factor in there. So that's why you'll have that. One other thing, okay, and I promise this will be my last comment, is you may have noticed something that we never pointed at. Namely, this number 4. We never actually had that number show up anywhere in our problem or any of our computations. Is that bad? Was a mistake made? And in this case, the 4 was a descriptor. It wasn't actually a measurement that really came into play. It's just saying we have this object, we're calling it the 4-pound roast. We could have just said a roast. And so the 4-pound doesn't make any difference in terms of the original model. Now, we could be more sophisticated and say, well, the roast doesn't cook evenly, the internal temperature versus the outside. But for right now, we're saying we're treating it as a single solid object. This will happen, especially when you start going into real world problems where you're going to be given a lot of information and you'll get a lot of numbers involved, and you have to decide, well, which numbers are the important ones and which ones aren't. And in this case, the 4-pound roast, the 4 is not an important number because it's being used to describe something, not being used to measure something. So it's good to try to get into that habit. We won't do that too often, but it's also important at this stage to be like, hey, did I use all the information, and which information is actually relevant? And the further on you go, you will discover you will have a lot of irrelevant information when you deal with real-world applications. And so you have to learn to be able to filter. All right. Okay. I think we said enough about this problem. Let's move on to some fun problems, right? They're all fun. Come on. Okay. So this is an important one. All right. The logistic model. So find y given that y prime is equal to minus k times y minus l, where k and l are constants, and y of 0 equals y not. All right, great. So this is used for various things. It can be used for a more realistic model of population, for instance. Okay, so let's begin. This should be interesting. All right, and we've done, by the way, we talked about the logistic model before, so we kind of know what the answer should look like. So getting to that, it's going to be a ride. All right, well, let's begin by separating. So we could say, hey, we have dy over dx is equal to minus k times y minus l. And, all right, it's not hard to separate. Dy over y times y minus l is equal to minus k times dx. All right, separation complete. Next up, integration. All right, integrate. Well, one of these two sides is going to be really easy. The minus k dx, because k is thought of as a constant because it tells us k constant. So this is going to be minus kx, and then we'll have some additional constant, c. The hard part is this integral over here. How do you integrate dy over y times y minus l? This is not so easy, but it is something that we've seen before. So when we took our Calculus 2, which is, what a great class, we learned how to integrate a variety of functions, including functions that looked like this. Now, I know you're thinking, boy, that's a long time ago. I don't even remember any partial piece of Calculus 2. Not even a fraction, you might say. All right, what's the right technique here? So, it's partial fractions. So let's recall what the goal is for partial fractions. The goal for partial fractions is to say, we'd like to pull things apart downstairs. So I don't want to have both y and y minus l. I'd like to have them separate. So I'd like to have something with just y and something with just y minus l. And so we say, okay, well, how do we pull things apart? Well, upstairs is super easy. Say, look, if we have addition upstairs, okay, pull things apart. Downstairs, you have to use a little bit of algebra. So in particular, we have the following. We say, look, this expression, 1 over y times y minus l, is equal to something. We don't know what it is. So we'll call it an A. A is an unknown constant for now, but we'll get to know it. So A over y plus some other unknown constant over y minus L. All right, so great. Now what do we need to do? Well, when we're doing partial fractions, the hardest part, and this is the first step, is getting the right form. So we have the form. The next thing to do, clear your denominators. Fractions, that's the hard part, right? So we'll get rid of the fractions. So that says the same thing as saying, hey, 1 is equal to A times y minus L plus B times y. So what happened here is we multiplied both sides by y times y minus L. So that's what just happened. We multiplied both sides by y times y minus L. So you see on the left-hand side, we get complete cancellation. That's where we get the 1. In the first term, the y's cancel, so we're left with the y minus L. In the second term, the y minus L's cancel, and we're left with a y. And I say, okay, well, now we're really close. And here we have, to figure out A and B. Now, but this is an expression which is true for every choice of y. And so I like to use the technique of choosing nice values for y. So we're going to choose, and we're going to choose wisely, because, a good choice will help us find the answer. Well, what are some good choices? Well, if we choose y equals 0, what will happen is it'll knock out the second term completely, because we have 0 times b. Well, that's 0. So we'll get 1 is equal to a times 0 minus L. So 1 equals minus L times a, or a is minus 1 over L. If we let y equal L, that completely knocks out the first term. L minus L is 0. So you say, okay, 1, the first term was gone, is equal to L times b, all right? Or we're going to say, great, that's b is 1 over L. And now we know A and we know B. So what this allows us to do is it says, hey, this expression, 1 over y times y minus L, I can rewrite as two separate pieces. And because we pulled it apart, each piece is easier to integrate. In some sense, the philosophy of integration is to say, hey, let's take our expression and find a way to simplify, break into small parts, each part of which is something we can work with. So that tells us that this integral here is the same as the following integral, namely the integral of a over y, so that'll be minus 1 over L times 1 over y, plus b over y minus L, so plus 1 over L times 1 over y minus L, and all of this is dy. We haven't done any integration. Partial fractions is not an integration technique. Partial fractions is a pull things apart technique so that the integrals become easier to do. And now, well, of course, the integrals have become easier to do, right? That was our goal, and I think we succeeded. So what do we have? This is minus 1 over L times log of y, and plus 1 over L, and here we have log of y minus L. And now we're good. We're wonderful. Okay, so let's keep going here, and let's see what we can say. So, switch our colors, because we've done a lot. And we say, okay, look, we have that this expression is equal to that expression. All right, well, that's fine. No problem. Let's multiply both sides by L. So we could say minus k times L times x plus L times c. Well, L is a constant, c is a constant, and constants absorb constants. So, all right, plus some constant c is equal to, we have minus log of y plus log of y minus L. But what can we do when we have logs? In particular, when we have logs being subtracted. Well, that's the same as log of the part that's being added goes upstairs, y minus L. Part that's being subtracted goes downstairs over y. Or if you like, that's the same as log of 1 minus L over y. Now, this is really good. We are happy. Now, you might say, I don't know if I'm happy, Steve. Tell me why I'm so happy. We're happy because how many y's do we now have? 1. 1 y to rule them all. 1 y to find them. 1 y to bring them all. And in the light of calculus, bind them, right? Because if we have a single y, now it's just a matter of just slowly and gently, lovingly massaging it to get that y by itself. Okay, so what are some things we can do? Well, we say, look, we want to get rid of the log because that's sort of the outermost layer where that y is. Okay, raise both sides to the exponent, right? E to the. All right, so we can say, all right, well, e to the natural log becomes 1 minus L over y, right? Because e and natural log undo each other, is equal to, now e to this, all right, well, that's e to the minus k times L times x. And then we have what? Well, e to the c. Well, e to the c is a constant, similar to what we've done before. So, okay, constants absorb constants. We'll just write it as some constant c. Okay, well now, what can we do? Well, we can move things around. We can do that, perfectly allowed. Okay, well, now, what do we have? Well, we'll have 1 minus this constant c, e to the minus k L x is equal to L over y. Let's flip both sides, and we'll have y divided by L is equal to 1 over 1 minus c e to the minus k L x, and multiply across, we get y is equal to L divided by 1 minus c e to the minus k L x. Aha! Good. Now, are we done? And why not? Well, we're getting close. What haven't we actually taken into account yet? We haven't yet taken into account our initial condition. Okay, so time to do that. So, in retrospect, you'll notice this is not a great place to solve for our initial condition, but we can come back up to this stage, because this constant is the same as that constant. Now, I will say, you have to be careful, because this constant is not the same as that constant. That's why you have to sort of keep track of, wait, what happened? So here, this was our final, our final absorbing constant stage. And if we plug in, what do we have? We can say, hey, look, we can say at x equals 0, we have that y is y0. So this tells us that 1 minus L over y0 is equal to c, e to 0, which is also just another name for just c, because e to 0 is 1. Or we could say, hey, c is y0 minus L all over y0. Okay, so that's what our constant is. So we say, okay, great. We can put that into there. And now if we do that, and if we multiply both top and bottom by our value, y0, we get the following expression. So y is equal to L y0, divide that by our y0 minus our y0 minus L e to the minus k L x. And there we go. Done. We made it. We were able to figure it out. And wow, that took some work. That took a lot of work. Now, you should check a couple of things. Okay, what happens if you do plug in x equals 0? All right, well, that part becomes 1. The y0 minus y0 cancel. The minus minus L becomes a plus L, so the whole downstairs becomes L. L over L cancels, and you're left with y0. So that's good. You'll also notice if you let x head off towards infinity, this part does what? Well, it goes to 0. So that says this last piece goes away, and you have Ly0 over y0, which means you go to L. And so in the long run, we go to L. So there we are. Great. So it matches what we think should happen under this model. And yeah, wow. A little bit of work, right? And that just goes to show you, even adding just a little bit extra, that one little extra piece, well, okay, a lot more work can go on. You can imagine if we add even a little bit more, then we're going to be like, okay, forget it. Hopeless. But we're able to make it work. All right, nice, good. Whew. All right, well, on to more simple things, we hope. All right. Okay, this one looks more straightforward. So, given that p prime is equal to t squared times p plus t squared divided by p squared, and p of the cubed root of log 2, so that's not a square root. See that little 3 there? That means the cubed root equals 1. That's kind of a weird initial condition. All right, find a general expression for p of t. Now, when you look at this problem, you might say, is this separable? Because we have these sort of pieces here, and the question is, can we separate? Now, keep in mind that when a problem is given to you, you have the right to rewrite it in a more simple way. In fact, not only do you have the right, in some sense, you have the obligation to do that. And so you should always sort of ask yourself the question, have they given this problem to me in a good way? And if not, you should say, well, how should I rewrite it to make my life better? Because that's what we want. We want your life to be better. So let's work on rewriting this problem. Okay, so we're given this p prime. All right, so let's see what we can do. So p prime, we'll write as dp over dt. So we're thinking of t as our variable here, is equal to, and now what do we see? Well, it's initially t squared p plus t squared over p squared. Well, what can we do? Well, notice they both have t squareds. So let's factor that out. So that is t squared times p plus 1 over p squared. And now we're much more comfortable. It's like, aha, this is clearly separable. Right here, not so clear, but here it's like, oh yeah, function of t, function of p. Okay, but let's go just a little bit further and say, well, look, we can add these together. Common denominator would be p squared, because this p is really the same as p over 1. So this would become t squared, and so I'd have to multiply the first term by p squared over p squared, giving us p cubed plus 1 divided by p squared. All right, now we do our separation. So we're going to take this term, bring it across, and we're going to flip it over as it comes across, so that we have p squared over p cubed plus 1 dp is equal to t squared dt. All right, so we've separated. Separation is good. And now, after the last problem, we might be a little bit nervous because we're like, uh-oh, partial fractions, Well, do we have to be nervous? Let's think about it. How would you integrate this? Because that's our next step. How do you integrate? Well, we have p cubed plus 1 downstairs, p squared upstairs. What can we do? Now, we could do partial fractions, but that doesn't mean it's a smart thing to do. What's a smarter thing for us to do? Substitution is smart. Why? Because look, if you set u equal p cubed plus 1, then we'll get that du is equal to 3p squared dp. Or, moving that 3 across, a third du is p squared dp, which says, hey, that's the upstairs. This is perfect for substitution. And we should always try substitution as one of the first things to look at. Substitution is such a powerful tool, and it's one of the easiest to use. So always try that early. So if we do this, we have what? Well, we have the integral. There's a 1/3 du. That accounts for the p squared dp. And then this p cubed plus 1 downstairs is a 1 over u. All right. Well, that's 1/3 log of u. Or if you like, 1/3 log of p cubed plus 1. Okay, so that's that side. The other side, well, that's not bad at all. That's 1/3 t cubed plus c. All right, now what can we do? Well, let's clean it up. Let's multiply both sides by 3 so we can get rid of our 1/3. So we now have the following: log of p cubed plus 1 is equal to t cubed plus c. And now you might say, wait, 3c? Well, this is the constants absorbed constants idea. And so I'm just sort of using that sponge of c. It's like, okay, well, let me get that 3 as well. All right, so that c has absorbed the 3. And now we're like, wow, beautiful, beautiful. Well, what do we want? Let's solve for c. We might as well. There's this crazy looking expression here, and it says, look, when we have I was going to say x, but it's actually t is equal to the cubed root of log 2, that p should equal 1. All right, that's our initial condition. So we have log of 1 cubed plus 1 is equal to the cubed root of log 2 cubed plus c. Well, all right, so that's log 2. And this is also log 2. Right? Because if you take the cubed root of something cubed, you get back what you started with. So you have log 2 is equal to log 2 plus c. So what is c? 0. All right, great. So that's nice. So I say, all right, we're almost there. We get log of p cubed plus 1 is equal to t cubed. And now we'll just unwrap. All right, there's only one p. So we start by exponential function. Say, okay, p cubed plus 1 is equal to e to the power of t cubed. Subtract p cubed is e to the power of t cubed minus 1. And then cubed root gets us that p is the cubed root of e to the power t cubed and minus 1. And we're done. That's it. Yeah. Wow. After the last couple of problems, we were kind of thinking, oh, okay, we're going to be here for a while. But actually, no, most of these problems go pretty quickly once you get the hang of them. And we had to do some challenging ones just because we were being very general. But all right, there we go. So let's try another problem. Okay, here's one. So, on their 30th birthday, an art history major opened an IRA account which has a return of 5% and started depositing $500 each year. All right, not a lot of money for a retirement account, but they are an art history major, so they're used to not having a lot of money, so that's okay. So if M is the number of dollars in the account at time t in years since turning 30, then give a differential equation for M, all right? And if the art history major retires at age 70, how much money will be in the account? All right, great. So differential equation time. Time for us to find a nice formula, differential equation. Oh, this will be good. Okay, so when we're talking about differential equations and setting it up, the way I like to go through the process is to say, okay, there's a derivative involved, and so we're really looking at how something changes. So in particular, we want to give a differential equation for m. So it says, all right, I want to know how does the money change. So there's this retirement account, and the question is, how is money changing? Well, we can say, look, there's two ways the retirement account grows. One way is that they put money in. So our money grows. There's 500. That's one way we grow. So this is the deposit. And then there's a second way that we grow, which is the interest, right? So they deposit 500 each year, and it has a return of 5%. Now, what does that mean? Well, that says however much money you have in the account, you get 5% more. And so what is 5%? Well, that's 0.05, or I would probably say 1/20th. 1/20th m. So this is your interest. So this is how much your money changes by. What's the change in the money? And it changes because of these two factors. How much do you get because of the deposit? How much do you get due to interest? All right. Well, great. That's it. That's the differential equation. So we're done. Now, there's a second part which says, okay, what if they retire at age 70? How much money will be in the account? Well, that means we need to solve. And all right, well, how to start? Well, one way we can do this is we can say, well, let's factor out the 1/20th here. We can do that. We're perfectly allowed. So 1/20th, and I'll put the m in front just because I want to. All right. Now, if you factor 1/20th out of 500, what will you have? So another way to think of it is 1/20th times what gets you to 500, and well, the answer is you'll have 10,000. Okay, so that's what you have. 1/20th times m plus 10,000. All right. Well, now we can do our separation, right? Because we'll think of this as our change in money with respect to time. That's dm dt. So we can say dm divided by m plus 10,000 is equal to 1/20th dt. All right, and now, well, we say, okay, integrate, and the left-hand side, that's the natural log, m plus 10,000 is equal to 1/20th t plus a constant c. All right, great. Now, use the exponential function here. We can say, okay, m plus 10,000 is equal to e to the 1/20th t. And then this e to the constant, well, that becomes a new constant, c. And we can say, okay, or we can say, look, m is equal to this constant, e to the 1/20th t, and we'll subtract 10,000. Okay, now we're almost there. We just need to figure out c. So what we'll think of is we'll say, look, in the account, we'll say at time equals 0, we'll have our m equals 0. So you're opening up the account has 0 at time 0. And by the way, time equals 0 is their 30 years old, because that's when they start the account. So we say, okay, great. So we can plug that in and say 0, e to the 0 is 1, is equal to c minus 10,000. And so that tells us c equals 10,000. So really we say, aha, our money at any given time, since these are both 10,000, by the way, we can write that as 10,000 times e to the 1/20th t subtract 1. Okay, so there's our money at any given time. Now that's not really an answer, so we shouldn't have boxed it, but it feels so good. We worked hard to get that. So what's the question? Well, the question is, okay, how much will there be? So what do we want? We want to know what happens at age 70. So we say, okay, at 70 years, which really means that our time is 40. Because we start at 30 years is when we start, time 0. So 70 years, they've had time equals 40, 40 years to have things build up. We can say, look, our money, well, that's equal to 10,000. And then here, we'll have 1/20 times 4. And then 1/20 times 40, that's, well, that's 2. So E squared, subtract 1. All right, and so that's the answer. Now, how much is that? I don't know off the top of my head. But we can say some really, really terrible computations, right? E is 2.71 something, something, something. And so E squared is less than 3 squared. So this is less than 9. So 9 minus 1 is 8. So this is definitely less than $80,000. And probably somewhere, I would say in the $70,000 range. So like I said, for an art history major, that's a lot of money. But who knows? Is it enough? Maybe for them, yeah. But that's the answer. That's it. Cool. So there you go. There you go. All right. Well, great. Let's keep going. More problems, right? Ooh, this is an essay problem. Now, the good news is usually the longer a problem, the shorter the answer, because we don't have a lot of space. So I really hope it's a short answer. So in 1962, a young girl at a boarding school in a rural village in Tanganyika, which is now Tanzania, started laughing. Her laughter quickly spread to her classmates, then to her village, and then to surrounding villages, and the epidemic of laughter continued for several weeks. This is an actual event. It's in the history books, and they've studied this. Now, suppose that we assume that we are more likely to start laughing in a laughing epidemic the longer we have been exposed to it, and at the same time that it spreads fastest when there are fewer people currently laughing. And we can say, well, what does that mean? Well, we can roughly capture this in the differential equation y prime equals minus 1 over 200 t times y, where y represents the total number of people who are currently not laughing, and t is time measured in hours. So we say, okay, well, say, look, how many people have stopped laughing? You know, that's what the y prime is capturing. How many people are stopping laughing? That's the y prime. And it says, well, it's some multiple of time. So the longer the time goes, the larger the decrease. And on the other hand, it says, okay, here, larger y, also the larger decrease. So if there's a lot of people who aren't laughing, well, okay, then that means that there should be a bigger change. If there's very few people who aren't laughing, well, very small change. And then, of course, always there's an extra constant in front, which is like a fudge factor. All right, so an epidemiology team, upon hearing about a laughing outbreak, where there were initially 40,000 people who were not laughing, rushes to investigate. By the time they arrive, there are only 5,000 people who are not laughing. How long after the epidemic broke out did the team arrive? So that's our question. Okay, so let's think about it. Now, we should always get into the practice of identifying what are we looking for, and we're looking for how long after. So this says we're really looking for some kind of a time. So our final answer should be a time, and in particular, it'll be some kind of time measured in hours, because those are our units, right? Time is measured in hours. All right. Well, let's see what we have. So we certainly have a couple of things. We have our differential equation, and we see it's really nicely set up for us to be separable. So let's go ahead and solve that differential equation. So we could say that we have the following: dy over dt is minus 1 over 200 t times y, or dy over y is minus 1 over 200 t dt. So far, so good. Well, what comes next? Integrate both sides, right? You separated. The next thing is you integrate. So we have natural log of y is, we integrate here, we're going to get minus 1 over 400 t squared plus, of course, some appropriate constant c. So from here, we can say, all right, let's solve for y. So we can say, all right, use the exponential function, and we can say y is equal to, and here you have that e to the minus 1 over 400 t squared, and e to a constant is a constant. All right, great. So, good. Now we have our nice expression other than what is c? Well, there's some information. So we have this word initially. So when you see words like initial or initially, those are initial conditions. So we have this 40,000 who are not laughing. Well, what does that tell us? Well, that tells us what is y at time 0. So we could say, aha, we can say when time equals 0, capital Y equals 40,000. So, well, that tells us that 40,000 is equal to c e to the 0. So great. So we know what c is. So we're doing great. So y is 40,000 e to the minus 1 over 400 t squared. So we're almost done. What's left? So now we say, okay, what are we interested in? Well, we're interested in at what time do we have 5,000 people who are not laughing? If we can solve for that, life is good. So let's go ahead and solve for that. And then life will be good. So let's see. Let's start over here. So we want 5,000. That's y. That's the number of people who are currently not laughing. Well, that's equal to 40,000. And then we have e to minus 1 over 400 times t squared. Okay, so we can divide. Take 5,000, divide by 40,000. The nice thing is there's lots of zeros there. So we can even cancel some zeros off before we do that, which really just means divide by 10. So it's really like 5 equals 40 times that. And, okay, 5 over 40 says, okay, this is the same as 1 over 8 is equal to e to the minus 1 over 400 times t squared. Take the natural log of both sides. And so we get the natural log of 1 over 8, which, by the way, there's this nice property of natural log which says, you know, natural log of 1 over something is minus the natural log of something. So this is the same as minus log 8 is equal to minus 1 over 400 times t squared. Well, all right. Now multiply both sides by minus 400. And we say, so t squared is equal to, the minuses cancel. We get 400 times natural log of 8. Or we say, t, well, square root, we get square root of 400 is 20, and the square root of natural log 8, well, is something, but it is what that is. So square root natural log of 8 hours. And so there we go. That's how long after the laughing epidemic broke out that the team arrived. And we're done. Wow. Cool. And all right. Well, if you wanted a better answer, of course, decimal answer, a good time to grab your calculator. All right. Good. Well, I have to say, laughing epidemics sound pretty good these days. I'd be happy to have a laughing epidemic. All right. Well, next problem. And this is one of my favorite problems. I wrote this problem many, many years ago. and it's about Sneetches. Now you might wonder, what are Sneetches? Well, it comes from a story by Dr. Seuss. And if you're wondering what a Sneetch might look like, it looks something like this. So here's a Sneetch. And, well, what's the question? Well, so it goes like this. Now, the star-belly Sneetches had bellies with stars. See, there's a belly there. The plain-belly Sneetches had none upon theirs. No stars there on those bellies. Then one day, Sylvester Monkey McBean came to town with his wonderfully wonderful machine. Just one pass through, hop on board, and you will have a star for sure. The Sneetches listened, and the Sneetches thought, and those who wanted a star belly stepped up and bought. Sylvester kept track of the proportion of Sneetches with stars, so that's the parameter p, and noticed with time, t, in months, that p prime equals 1/3 t times 1 minus p squared. Very good businessman. You should always be keeping track of things with differential equations. Now his business was quick. He did not want to delay. And so he recalled on his very first day that p equals 1/4. So that means initially when he showed up, 1/4 of the Sneetches had stars. To make a quick buck and then leave this place, he decided to leave when p equals 3/4. So how many months then will it take until Sylvester McMonkey McBean leaves this place? Whoa. All right, what a problem. What a fantastic problem. Let's solve it. All right, so again, what are we after? Well, we want to know how many months. So we're after some time measurement in months. Now, how many months to what? Well, really, the question is, when do we hit 3/4? So initially, there was 1/4 of the population had their stars. It says, okay, look, when we get to 3/4, 75% of the population having stars, time to get out of here. My machine is not going to sell as many as it did before. So where to begin? Well, let's start with the differential equation because it's given to us. So we have this nice differential equation, and wow, what an amazing thing. It's actually separable. Well, that's not that surprising. And let's see what we have. We say, okay, we have dp over dt is 1/3 t times 1 minus p quantity squared. All right, well, let's move stuff around. And we can say, all right, we can say dp divided by this 1 minus p squared is equal to 1/3 t dt. All right, and now integrate. So integrate. Okay, so this side, it might throw you off a little bit. How do you integrate 1 over 1 minus p squared? Now, you can do a couple of things. You could do some use substitution. U equals 1 minus p. Or you could say, look, basically it's like u to the minus 2. And if you did all that, so we'll go ahead and run the computation through. So this is minus dp. So this would become the integral. There's no minus there, so this would become minus du. Minus du. And this becomes u to the minus 2. And all right, that's a pretty straightforward integral. The downstairs becoming a minus exponent. And so this becomes a minus u to the minus 1. And then you divide by minus 1. And of course, minus becomes pluses, which is 1 over u, which is 1 over 1 minus p. So if you're being very cautious, that's what you would do. Or if you'd say, well, the 1 minus p is basically like u, and so it's like 1 over u squared, you would still, you could reason it out without too much difficulty. All right. On the other hand, this other integral, well, there's hardly any surprise at all. That would be 1/6 t squared plus c. So there we go. Now, let's see where we're at. We have the following, namely that 1 over 1 minus p is equal to 1/6 t squared plus c. All right, well, what do we need now? Well, we probably want to have C. Okay, so let's solve for C. We can do that. We know our initial condition, right? Very first day, that's at time 0, p equals 1/4. So at time 0, we have p equals 1/4. And we say, okay, great. Well, 1 minus 1/4 is 3/4. Turn that over, and we'll have 4/3 equals 1/6 times 0 squared plus c. So we get c equals 4/3. Great. All right, so now we're to the following. 1 over 1 minus p is equal to 1/6 t squared plus 4/3. Well, what to do next? Now, the tempting thing, which we're not going to do, is to say, hey, let's solve for p. Seems very logical, because that seems to always be the case. But we don't have to actually solve for p. What do we have to solve for? What is it we're after? And if we can understand that, that helps give us insight into what we're allowed to do and what we're not allowed to do. Now, in our case, we say, well, hey, the thing that we're after is the time. And in particular, the time that we're after is saying, at what time do we get up to 3/4? So we can just say, look, let's just leave this expression as is and say, all right, now we're going to do the following. We'll plug in our expression where we have p equals 3/4, and then we'll solve for t. All right, well, let's do that. So if we plug in 3/4, 1 over 1 minus 3/4, what will that give us? Well, that's going to be 1 over 1/4, or that'll give us 4. So that's 1 over 1 minus p, 4. That's equal to 1/6 t squared plus 4/3. Okay, or if you like, we could say that 1/6 t squared is 4 minus 4/3. Well, what is that? Well, if you think of 4, that can be thought of as 12/3. 12/3 subtract 4/3 would leave us with 8/3. Or we could say, hey, multiply both sides by 6. That would say t squared. Well, that'd be 48 divided by 3, which is 16. Or take the square root. T equals 4. 4 months. Nice. Why do I love this problem? Well, I love this problem because first off, it has such a clean answer, 4 months. When you see this problem initially, it's like, it's not so clear you can end up with such a nice answer. The other thing I like about this is it feels like we kind of skipped a step. We didn't solve for p. But keep in mind, think about what the problem asks you to do, not necessarily what you're used to doing. And you can say, is this an important step, or is there an alternative? Be open to alternatives. There's nothing wrong with solving for p first, and then going through and solving for t. But you really want to say, hey, is this helping me, or is this not? And of course, I really love the fact I was able to write a problem involving Dr. Seuss. This is so good. Yeah, I don't know if I'll ever top this one. Well, I'm still not entirely. There's still, it's not all great in this beer. Perhaps someday. All right. Well, lots more problems to do, so we got to keep going. Okay. All right. Suppose the weight of a cloud in tons after t hours, denoted W of t, so W is weight, and decreases proportionally to its surface area, and that this process speeds up over time until the cloud is completely gone. We can approximate this behavior with the differential equation, W prime equals minus 5/3 t W to the 2/3. So we have this, there's this sort of that proportional, there's this constant. T is time, so the longer that we go, the faster the decay goes, so it's going to speed up as time progresses. then you have this w to the 2/3. And you might say, well, does that really make sense? And in some sense, why to the 2/3 power? You can think of it as sort of a volume versus area comparison, where you say, okay, volume is like 3-dimensional and area is 2-dimensional. So how do you go from something where it's 3 to something which is 2? And that's where the 2/3 comes into play. That's very hand-wavy, but it's actually not an unreasonable exponent given what we're trying to capture. So, given that the cloud initially weighs 1,000 tons, how many hours until the cloud is completely gone? So this is very similar to the previous problem. Not as fun to talk about out loud. So, since we've done the previous problem, let's do this one at a little bit more of a pace. So we can say, okay, change in W with respect to time, minus 5/3 t, w to the 2/3, or we could say dw, and then when this comes over, well, let's just write it as w to the minus 2/3. You know, we're divided by w to 2/3, it's w to the minus 2/3. Okay, that equals minus 5/3 t dt. All right, so there's our separation. Very quick, very straightforward. All right, now we do our integration. So we integrate both sides. Well, no tricky thing here. All right, to the minus 2/3, well, what would we do? Add 1 to the exponent, we'd have 1/3. Divide by 1/3, it's the same as multiplying by 3. So 3, w to the 1/3. All right, over here, that would be minus 5/6 t squared plus some constant c. All right, now what do we know? Well, we know that initially, all right, so that's initial conditions. So at time equals 0, we can say that w is 1,000. Well, all right, let's solve for c. All right, w to the 1/3, 1,000 to the 1/3 power. The cubed root of 1,000 is 10. So we'll have 3 times 10, which is 30, is equal to minus 5/6 times 0 plus c. So we now know what c is. C should be 30. All right, great. So we have 3 w to the 1/3 is equal to minus 5/6 t squared plus 30. Now, what's our question? How many hours until the cloud is completely gone? When do I know the cloud is gone? Well, what's the weight when the cloud is gone? All right, well, the answer is really weight should be 0. So for what time t, that's what we're after. We're after a time t, does w equal 0. So let's go ahead, let's plug that in. And if we do that, we'll get 0 should equal minus 5/6 times t squared plus 30. All right, we move things around. So 5/6 t squared equals 30, or divide by 5, multiply by 6, we get t squared equals 36, or square root t equals 6. So 6 hours. And we're done. We're done. Cool. Now, you might have the question that says, well, what happens after 6 hours? Because does that say the weight becomes negative? And, well, no. Really, it says, look, there's this differential equation works until the cloud is completely gone. And so once we actually hit that time, 6 hours, once that w equals 0, then it says, hey, this process no longer works, and there's nothing to lose anymore. So this is really a piecewise differential equation. It says w prime behaves one way while there's still cloud left, and when there is no cloud, w prime will be 0. Now, what it wasn't said is like, well, when does that happen? So, but now we know the answer. So w prime behaves in this fashion up till 6 hours, and then after 6 hours, there's no more clouds, so w prime equals 0. So that's That's what's going on. All right, well, see, after you do one, the next one's pretty quick. And that's why we do problems. Because as we do more problems, we get really good at doing them, and the following ones are just start going, and it's amazing how fast we can go. Amazing, amazing. All right, well, let's do a couple more, right? Okay. So, the Meeseeks are generated from a special box to help the Smith family solve a problem. In the process of solving a problem, the Meeseeks can generate more Meeseeks, leading to a large number of Meeseeks. So let m of t be the total number of Meeseeks which have been generated at a given time t. Or, if you like, that's the population of the Meeseeks. So this is somehow we're looking at a population problem. So the rate of change of the population of the Meeseeks is 10 times the product of the current number of Meeseeks together with e to the minus t. Now, why? Well, that indicates that Meeseeks are less likely to make more Meeseeks with time. So as time goes forward, they're like, well, we don't need quite as many as we did before. So this can be written as a differential equation, dm dt, which is m prime is 10 m e to the minus t. So given that initially there is exactly one Meeseeks, what is the number of Meeseeks there will be as time goes towards infinity? So in the long run, how many Meeseeks are going to have to be created to help solve this problem? Well, all right. Doesn't seem so bad. So let's start. They gave us a differential equation. They gave it to us as a sentence, and then they were even nice enough to give it to us as a formula. Wow, that was very nice of them. So we have dm dt is 10 m e to the minus t. We do our separation. We say, all right, dm over m is 10 e to the minus t dt. Integrate both sides. We'll get log of m is equal to minus 10 e to the minus t plus c. Now, we have some initial conditions. Let's use our initial conditions. We're told that initially at time 0, there's one Meeseek. So log of 1 is equal to minus 10 e to the minus 0 plus c. Well, what's log of 1? 0. Gone. Wow. And e to the minus 0 is e to the 0 is 1. So we say, aha, so c equals 10. Okay. Great. So now what? Well, we now need to solve for m. All right? So we have m is equal to e to the minus 10 e to the minus t plus 10. Okay, so there's the number of Meeseeks at any given time. So there's an exponential function inside of another exponential function. So wow, okay, lots to process here. Or maybe not so many things to process. So we say, okay, time marches on. Time goes to infinity. So we say, look, time only shows up in one place right there. And we say, look, that's e to the minus that. Well, what's that going to do? E to the minus a large number is doing what? It's going to a very small number. So this part is going towards 0. All right, well, wonderful. That means the minus 10 times something going towards 0 also goes towards 0. And what's left is 10. So we say, as time goes to infinity, the number of Meeseeks is going to approach the value e to the 10th power. And there you go. That's the answer. Haha! That wasn't so bad. Wow. Well, that's because we're not humming and hawing, right? We did a lot of humming and hawing in the earlier problems. But of course, once we get used to it, well, we can go pretty quick. All right, next example. It has recently been revealed that the reason that Twinkies have such an incredible shelf life is due to a rare molecule known as Twinkonium. Now, each Twinkie contains 5 grams of Twinkonium when first produced. Unfortunately, the Twinkonium then starts to decay and turn into ordinary sugar. Through extensive research, it has been determined that the rate of decay satisfies t prime equals minus 1/10 t squared. So we have this nice differential equation where time t is measured in months. If a Twinkie is still good when it has at least 1 gram of Twinkonium, how many months from when it was first produced will the Twinkie go bad? All right, if there has been ever a real-life application of differential equations, surely this must be it. All right, now you might say, aha, this is kind of like radioactive decay, right? Well, radioactive decay would be if it was just minus 1/10 t. This square changes it a little bit. So it's not some sort of exponential function. Well, how does it change things? Well, we should say, okay, look, the change in Twinkonium with respect to time is minus 1/10 t squared, or rearranging, we can say t to the minus 2. In fact, we can even put a minus, bring that across. Minus t to the minus 2 dt is 1/10 dt. All right, that's our separation. Now you might say, why'd you bring the minus across? Anticipation. I'm anticipating the next step. And if we hadn't, no problems. Still would have worked fine. So what do we have? Well, when we integrate this, we have a t to minus 1. Then we divide by minus 1, and that gets rid of the minus. So really, this left-hand side is t to the minus 1, or 1 over t. On this side, we get 1/10 t plus, of course, some constant c. Now, how do we solve for our constant? Well, to do that, we just say, well, what's going on? Well, we have some information, right? We say, look, each Twinkie contains 5, that's a number, when first produced. So that says, okay, we have when the time equals 0, that's the first produced, there's 5 grams of Twinkonium. All right, so that tells us that 1/5 is equal to 1/10 times 0 plus c, or if you like, c equals 1/5. Okay, so great. So we can update 1 over t equals 1/10 t plus 1/5. Now, what are we after? Well, we're after the question, all right, how many months will the Twinkie go bad? Well, when does it go bad? Well, it's good when it has at least 1 gram. So that borderline case is when do we hit that 1 gram measurement? So we really can phrase this as, all right, for what t, where t is time, does the amount of Twinkonium equal 1? If we know that, that's the borderline between a good Twinkie versus a bad Twinkie, of course. A bad Twinkie, who'd ever heard of such a thing? All right, so great. So now we have a plan. Plug in capital T becomes 1 and solve for lowercase t. So we say, all right, 1 is equal to 1/10 t plus 1/5. Well, let's multiply everything by 10. Okay, we can do that. And if we do that, what do we get? We'll get that 10 is equal to t plus 2. Or 10 minus 2 is 8. So that says, all right, it'll take us 8 months. All right, good. Now, disclaimer, Twinkonium is not a real thing. Do not wait 8 months to eat a Twinkie. I think it might go bad after like 7.5. No, I'm just kidding. Follow the use-by dates on your packaging. All right, good. Well, all right. Let's do another one. Okay. Find y, given y prime equals y to the 4th times 3x squared plus cosine of x, and that y of 0 equals 1. Okay, great. This is no more word problems, right? Good. Back to just like straightforward, no surprises. Let's just do it. So yeah, let's just do it. So we could say, okay, notice we're perfect, right? That just involves y. That part just involves x. So, and we have, of course, over here dy dx. And what do we have? Well, all right, we have y to the minus 4. So we're bringing that y across, which is really the same as divided by y to the 4th. dy is equal to 3x squared plus cosine of x dx. All right, now integrate both sides. We've done our separation. Next comes our integration. Integral of y to the minus 4, well, that'll be y to the minus 3. Then divide by minus 3, which is the same as multiplying by minus 1/3. All right, equals, on this side, well, integral of 3x squared, x cubed. Integral of cosine, is it sine or is it negative sine? Yeah, it's positive sine. All right, x cubed. Now, if you're never confident, just take a derivative and say, okay, what's the derivative of sine? Oh, the derivative of sine is positive cosine. Oh, yeah, it works. Okay, good. And then, of course, plus c. And now we can use our initial conditions. Initial condition says when x equals 0, y should equal 1. So this will tell us minus 1/3. 1 to any power is 1 is equal to 0 plus 0, because 0 cubed is 0. Sine of 0 is 0. And then equals c. Great. So we have minus 1/3 y to the minus 3 is equal to x to the 3rd plus sine of x minus 1/3. Okay, let's multiply both sides by minus 3. And so if we do that, we'll get that y to the minus 3, which is, by the way, the same as 1 over y cubed. Well, that would equal minus 3 times minus 1/3. That will become 1. So this 1 comes from there. Then minus 3x cubed minus 3 sine x. Now, flip both sides. Y cubed is 1 over this expression. And the last thing to do is get rid of that cubed, which we can do by doing a cubed root. So y is equal to the cubed root of 1 over 1 minus 3x cubed minus 3 sine x. And there you go. There we go. Wow, what a problem. What an amazing problem. But you know, it's good to practice these things, and it works out, right? Yeah, it does. But you have to practice it, right? And the more you practice it, the better you get. All right. Well, good. And I think one more. Let's do one more problem. Okay. Find y given y prime equals 1 plus x plus y plus xy, and y of 0 equals 2. Now you look at this and you're like, aha! This problem snuck in somehow by mistake. This is not separable. What is this doing here? Waiter! No. This is actually a separable problem, but it may not look like it. So that's the thing, is problems don't always look like what you expect them to look like. We always have the right to say, hey, can we rewrite this? And we look at the left-hand side, this 1 plus x plus y plus xy. We start to say, well, can we do anything here? And yeah, we can. We can absolutely do something here. We say, well, look, it kind of, as it is, it looks a little bit tricky, but notice, for example, the y's here, if you factor out the y's to the last term, you have a 1 plus x. You say, well, wait a second. This is a 1 plus x at the front. We say, what? Well, that means it's really, if we pull the 1 plus x out, it's 1 plus x times 1 plus y. So the key here is that, this is factorable. And by factoring, now we get something which is workable. So we have dy over dx is equal to 1 plus x times 1 plus y. And now we're off to our races. So dy over 1 plus y is equal to 1 plus x dx. And our separation is done. Well, all right. Next up comes integration. So we integrate. On the left-hand side, that one we can do. That's log of 1 plus y. If you're not comfortable, you could do a substitution equals 1 plus y, but this one is not too bad, so we'll skip that step. Over here, x plus a half x squared plus c. All right, well, what do we have? Well, it says, look, when we plug in 0, we should get 2 out. That doesn't look like we're going to have nice numbers right now, so let's hold off solving for a constant for just a moment. We'll come back. And now, well, let's free the y. All right, so e to the log 1 plus y is 1 plus y is equal to, over here, well, we'll have e to the power x plus a half x squared, and then we'll have e to the constant. And let's just say, hey, we can rewrite that as a constant in front. This is our constants absorb constants kind of mindset here. Or, if you like, we can say, look, y looks like some constant c, e to the power x plus a half x squared up in the exponent, and then minus 1. All right, now we're not done because we need to solve for c. And we sort of hummed and said, it's not looking great. Well, we got to bite the bullet at some point, so let's do it now. So we have that when x equals 0, y equals 2. So 2 is equal to some constant c, e, and 0 plus a half times 0 squared is 0 minus 1. Well, e to 0 is 1. And then we can add 1 to both sides. C equals 3. So, substituting that in, we come to our final answer. Say, aha, y has the form of 3 e to the x plus 1 half x squared minus 1. And we're done. All right, that was a lot of practice, probably more than we needed, but can you ever have too much? Maybe. All right, well, on to bigger and better things in the near future. See you again.